Good day, everyone. My name is Mahid Mangontarum from the Mindanao State University. Join me as we take a brief introduction to one of the most challenging yet interesting field in mathematics known as graph theory. In the early 18th century, the Prigel River in a city called Königsberg surrounded an island before splitting in two. 7 bridges crossed the river and connected 4 different land areas. Many citizens of the time attempted to devise a walk through the city that would cross each bridge and return them to the starting point without traversing the same bridge twice. However, none of them could do it no matter where they chose to start. This then gave birth to a historical notable problem in mathematics known as the 7 bridges of Königsberg. In 1736, the Swiss mathematician Leonhard Euler proved that it is in fact impossible to walk such a path. His analysis of the challenge laid the groundwork for a branch of mathematics known as graph theory. Graph theory nowadays is often defined as the study of graphs, which are mathematical structures used to model pairwise relations between objects. A graph in this context is made up of vertices or nodes or points which are connected by edges, arcs, or lines. Graphs are one of the prime objects of study in discrete mathematics. Mathematically, we define a graph G as a pair of disjoint sets V of G and E of G, where V of G is a non-empty set of points called vertices and E of G is a set of lines called edges. Here, V of G is the vertex set of G and its cardinality is the order of G. Similarly, E of G is the edge set and the cardinality is the size of G. An edge E joining the vertices U and V is usually denoted by this notation, or we can simply write E equals UV. If E equals UV, we say that U and V are adjacent and are ends of E. We also say that E is incident with U and with V. Moreover, if E equals UV and U and V are distinct vertices, E is a link. An edge E joining a vertex onto itself is called a loop. Finally, two or more edges joining the same pair of vertices are called multiple edges. Here is an example of a graph. As we can see, the edge E sub 7 is a loop since it joins Y onto itself. The edges E sub 1 and E sub 2 are multiple edges, while E sub 3, E sub 4, E sub 5, and E sub 6 are links. The vertex U is adjacent to V and W. Vertex W, on the other hand, is adjacent to U, V, X, and Y. Since there are 5 vertices in this graph, the order is 5, and because of the 7 edges, the size is 7. Now, a graph H is called a subgraph of a graph G, denoted by this notation if the vertex set of H is a subset of the vertex set of G and the edge set of H is a subset of the edge set of G. Here is an example. Notice that the vertices and edges of H are all in G. In this case, H is a subgraph of G. Given a graph G, a vertex labeling is a function of the vertex set of G to a set of labels. A graph with such function defined is called a vertex labeled graph. Similarly, an edge labeling is a function of the edge set of G to a set of labels. In this case, the graph is an edge labeled graph. When the labels of the edges are members of an ordered set, it may be called a weighted graph. Here are some examples. Notice that the graph in the left is an edge-labeled graph, while the graph in the right is vertex-labeled. A special case of graph labeling where there is an assignment of labels called colors to elements of a graph subject to certain constraints is called graph coloring. There are three types of coloring in graphs, namely vertex coloring, edge coloring, and for planar graphs we have face coloring. When used without any qualification, a coloring of a graph is almost always a proper vertex coloring, namely a labeling of the graph's vertices with colors such that no two vertices sharing the same edge have the same color. We may also define a vertex coloring of a graph G to be a mapping C from the vertex set of G to a set S containing the integers 1 to k such that the image of V sub 1 is not equal to the image of V sub 2 whenever the vertices V sub 1 and V sub 2 are adjacent. It is important to note that the elements of S are the available colors. We define the smallest integer k such that the vertex coloring C exists to be the chromatic number of G. And when the chromatic number of G is k, where k is less than or equal to an integer h, then G is h colorable. This is illustrated in these examples. Finally, an edge coloring of G is a map C from the edge set of G to S such that the image of E sub 1 is not equal to the image of E sub 2 for any adjacent edges E sub 1 and E sub 2. The smallest integer k for which an edge coloring C exists is called the chromatic index of G.